Okay, here's a couple rules about light. This is reflection and refraction. This is really easy, really straightforward. Only a couple little formulas to think about here. But first one is about the reflection of light. You have probably observed that if a pool ball or some kind of physical object comes in, strikes a table at a certain angle, it's going to bounce out at that same angle over here. If this is a 40-degree angle, this has got to be a 40-degree angle. We always measure off of that normal line, that perpendicular to the table edge there. Okay, if you bounced a ball off the ground, it would come and change its direction so that this angle is equal to that angle right there. Well, the same thing happens with light, and that's one of the things that got people thinking about light as a particle. But that angle of incidence has got to be equal to the angle of reflection. And that's really the only rule that you need down there. Sorry about that. Theta sub I, the angle of incidence, equals theta sub R, the angle of reflection. And so that's pretty straightforward. I guess I could do an example for you if you really need me to. There's a couple different kinds of reflections. If everything bounces smooth, if it's a super smooth, flat surface, then you're going to get specular reflection. If it's all bumpy and lumpy, then that normal line is changing every time that here we're headed uphill, so the normal line is going to be something like that. And you can see that the angle over here has got to be equal to the angle there. So as the angle of the surface changes, then the normal line changes, and that makes the lines go off in all kind of crazy directions. But if it's a nice smooth surface, the normal lines are all perpendicular to that flat surface and everything goes out parallel. All right. With plane mirrors, you know that the image is left-right reversed, but not up-down reversed. When you look at yourself in the mirror, your head is on the top and your feet are on the bottom. But if you wave with your right hand, it appears that there's someone waving at you with the left hand. So again, you're right side up, but you're reversed left to right. And we could draw some pictures and show why that is. But the image seems to be as far behind the mirror as you are in front of it. That's called a virtual image. It's not really there. There's nobody behind the mirror waving at you. It's a picture that gets put together in your eye, in your brain. And so that's that virtual image thing. We'll see more virtual images as this goes on. Now, this is a ray diagram. This is probably the easiest ray diagram we could draw. But what we want to do is to think about light coming from the object. Maybe the sun was over here and it bounced off the top of this thing, gathered a little bit of that color and carried it with it this way. It bounced off of a mirror or a wall or something and into our eye. Our eye sees that little bit of color coming in, and it traces that ray backwards. Say, where did that come from? And it just kind of draws a straight line here. It appears that it came from over this way. If I had a couple of these rays that were at a slightly different angle, then those two rays would hit the mirror, come into my eye would trace them both backwards, and because there's two rays at a slightly different angle, they're going to meet over there, and that's the point where it maps it to. So I get that three-dimensional appearance from these multiple rays entering my eyes. Also, because I have two eyes that are, a couple inches apart, I get a parallax thing going on with, and I can see that three-dimensional a little bit better. But there again, you see that this is the object. This would be the virtual image over here. It wouldn't really be blue. It'd be the same color as, I don't know why they made it blue. But that is a ray diagram where we're thinking about the rays that could come off and what happens to them and why it looks the way it does. Now, if you think about this ray diagram, you can see why the object is not up-down reversed. The chess piece on the left is upright and the virtual image is upright. It didn't reverse, it didn't flip it upside down because of what you see there, because of the ray. It comes up and it's going to map to right there. If I had taken one of the bottom rays, let's say that a ray of light left the bottom here and it came and it hit the mirror and it bounced at the angle of incidence equals angle of reflection and comes into my eye is going to chase that thing backwards over here. and it's going to map the bottom of that chess piece to right there. So the bottom maps to the bottom, the top maps to the top, and everything's good. Let's say that this is my right shoulder and this is my left shoulder, though. I wave at myself in the mirror with my right hand. That light comes and hits the mirror, goes into my eye. My eye draws that line, and it comes over here, and it appears to be on my left now. As I look at it, that would be like somebody's left hand waving at me. So that's the reason that it's left-right reversed, but not up-down reversed. Okay, we'll draw more of these ray diagrams. They get a little bit more interesting with curved mirrors and curved lenses, but we'll see that. A lot of times physics books will throw a problem in there, say, how big of a mirror do you need? If you want to see your whole body, do we really need a full-length mirror? And the answer is no, we only need a half of a length mirror. If we think about the light coming up from our feet, it's going to hit at point B and bounce into our eye. We don't really need any mirror below point B. And the same thing on the top. Here's the top of my head. Well, it doesn't quite look like that, but comes down. The light's going to hit about halfway between the top of my head and where my eyes match up, and then bounce into my eye. So I don't really need anything above that point either. And I could chop all that and all that off, and that would work out to height half of my height. Even if I back far away or come up close, it's still going to be at those 2 points. They haven't said anything about the distance this way, and it doesn't matter. Get a little mirror and try it out and see what you think. Okay. Now, that was reflection, when light bounces. This is the rule of refraction, and this one's almost as easy as the other one. Right here, if I have light that's traveling, let's say in air, and it moves into a glass tabletop, for example, and then goes through the bottom of the glass tabletop, you see how the path of the light is bent at every juncture, at every interface between the two mediums. Up here I've got air, here I've got glass, and the light bends right there. When it goes from glass back to air, it bends again. And there's a rule here. The first formula in this stuff, I guess, that we've seen called Snell's law. N1 sine 1 sine theta 1 equals N2 sine theta 2. And that's the only rule that you really need here for this. You do have to know what N1 and N2 are. And those have to do with the material that you're traveling in. This little table here shows you that the N, the index of refraction, for vacuum or air is 1. For water, it's 1.33, ice 1.31, glass is about 1.5, and diamond down there at the bottom is 2.4. Okay, so once you have that number, then you can go and work Snell's law. Now, I should tell you how they got that number. N is the ratio of how fast light travels in vacuum compared to how fast it travels in the material. When light goes into glass, it slows down. When light goes into water, it slows down. When in vacuum, it travels faster than anything else. That's our 3 times 10 to the 8 meters per second. Okay, so if light were to go into glass and slow down to say 2 times 10 to the 8 meters per second, then to get the index of refraction of glass, I'd simply say the speed of light 3 times 10 to the 8. And divide by the speed of the light in the glass, 2 times 10 to the 8. And the 10 to the 8s would all cancel, the meters would all cancel the seconds. And I just have 3 over 2, which would be 1.5. Okay, so that's how they got those numbers right there. In practice, we're going to go to the book and look it up, or I'd give them to you on a test or something. And then you'd be ready to put those into Snell's law right there. Okay, so this formula is worth writing down, and I suppose this would be worth writing down too. They could say the index of refraction in a material is 1.8. What is the speed of light in that material? And so then you put a 1.8 here, you put 3 times 10 to the 8 there, and you solve for V. So that's not hard either. Both of those probably worth writing down somewhere. But this is the way light acts. When it comes here, and it hits a material with a higher index of refraction, it's going to bend so that the angle is smaller, closer to the normal line. And when it goes from a material that has a high index of refraction, say glass, into a material that has a lower index of refraction, like air, it's going to bend away from the normal line. Snell's law measures those angles for us. We're going to do some examples here in just a second. A little trick people talk about, a way to remember this is think about a car that's driving here on the road and it hits a concrete curb, okay, or a mud, or maybe it's a line of soldiers marching, and they this side of, picture a width here to it. The bottom side of this car, the passenger tire, is going to hit the curb before the driver's tire, and so it's going to jerk the car closer to the normal line. Similarly, if it was hard to drive here and it comes out, the passenger wheel gets out first, and so it's going to speed up more than the other one, and it bends the other way. If that helps you remember which way it goes, that's fine. It's not really what's happening, of course, but it's a good way to kind of keep that in your mind. Let's do a couple of the examples here. And right here, the one on the left says that light is traveling in air, enters a glass tabletop at 30-degree angle. That's relative to the normal. If they don't say that, that's what they mean. We always measure relative to the normal. And they want to find the angle that it travels through the glass. So you can see that they put Snell's law there, N1 sine theta 1 equals N2 sine theta 2. We want to solve that for theta 2. So I need to get rid of the N2. I've divided both sides by N2, and it pops up on the left on the bottom. And then I got to get rid of sine, so I take the arc sine of N1 sine theta 1, divide that by N2, and that'll give me theta 2. We put the numbers in there, and it's going to travel at a 19.5-degree angle. It started out moving in air at a 30-degree angle. When it's moving through the glass, it has bent, and now it's a smaller angle. It's closer to the normal because the index of refraction is higher. If it comes back out the bottom, you could use that 19.5, put the angles in there. You do have to keep the indices matched up. Let me go back to this picture for just a second. See how the light was here? So this is region 1, and I've got N1 theta 1, and then it moves into region 2. So I need N2 1.5, and theta 2 would be the angle over here relative to the normal. If I were to go into a third region, I would number this number 3, and then talk about the index of refraction of region 3 and the angle that it's traveling in region 3. Like that. All right. Here's a second one. Light is traveling in air, enters an unknown material at 30-degree angle, and refracts at 11.5 degrees. So this must be even higher than glass because it's bent instead of a 19-degree. It's even closer to the normal line. So right here they wanted to say, well, what is the index of refraction of the second medium? We solved for N2 right there, put the numbers in, and it came up 2.5. So that's diamond. I think diamond's actually 2.4. I probably put the wrong number in. But you could do it like that. And they do that in the diamond store. They have a little box with light, and it shines in and shows the angle that it bounces out at. And then you can tell if it's a diamond or if it's fake or something. Here's an interesting case of this. This is referred to as internal reflection, but it's also refraction. It's a little bit of reflection, a little bit of refraction. The trick on this one is that the light is down in the water. So again, I would name where the light started region 1. That would be in the water. It's traveling upwards towards the air. That would be region 2. So I'd have N1 for the water, 1.3. And N2 would be the air, 1. Okay? But what they're showing there, those lines at different angles there, some of the light's going to go straight up. And when it does, some of the light will be reflected straight down off the surface of the water, and most of it's going to go straight up into the air. At that next angle, maybe there's I don't know, 40 degree to the normal line there or something, and there's a little R up above it. It's going up at an angle, Again, some of it will be reflected downward off the surface of the water, off the bottom of the water. How do you say that? The bottom of the surface, that interface between the water and the air. Get an internal reflection there. And some of it is refracted up into the air, and you could use Snell's law right there and see what R is. And but that third one is interesting, not the one that goes straight up, not the second one that goes, and there's the I and the R. Right there, that third one goes at some kind of angle, and it's got it marked C there. C is for the critical angle, and there is an angle at such that all of the light is either reflected back down into the water or travels perpendicular to the water. And all you got to do is put in theta 2 in the air, put a 90 degree right there, and solve Snell's law, and you'll end up with a little critical angle formula there. So I could come in over here, and I could say the critical angle, theta sub c, is equal to the arc sine of N2, remember, up here's N2, where the light goes second, divided by the index of refraction. Down here, that was the water, so 1 down there. So that'll give you that angle, and you can do that. If you try to do that and get your angles backwards, you'll know really quick, because you'd be trying to do, give me the arc sine of something larger than 1, and that's impossible, right? So right here, I'm doing the arc sine of N2, that's air, 1, divided by the water, 1.3, and I get about a 50 degree angle. When this angle right here is 50 degrees, then all of that light stays in the water. None of it goes up into the air. If you were walking along right here, you wouldn't see the light right here, because it all stays in. This light would be invisible down there. Okay? And of course, if you get bigger than the critical angle, it still stays down in there. One big industry application of that is fiber optics, and you see some fiber optic cables there. It's a little glass strand, and we send data communications down a fiber optic cable, and the nice thing is that all of that light travels in the pipe, in the little strand of glass, and there's no resistance, there's no heat. It's very fast, it's traveling at the speed of light, so you can carry a whole lot of data very quickly with no real loss of data or signal or anything else. So this internal reflection's got some good applications. Right here, when things are underwater, they appear to be higher, and they appear to be closer to us than they really are. So in this one, they you can see that I'm not sure I said that right. They appear whatever. Here's the chest. There's treasure chest, I guess, on the bottom of the water. You think about the light starting at the treasure chest, and it's going to come up here and go into our eye. It refracts when it goes out of the water. You could use Snell's law then find that angle right there. But what this thing kind of already does for us is it shows us that the depth that it appears to be, the apparent depth, that would be here, over the actual depth, all the way down there, is equal to that ratio N2 over N1. And so the thing is really much deeper than it is. Also, if you see this light coming this way at you, you're going to draw that line straight back, and you're going to think that it's over here, except you think it's on the bottom. So, really you think it's on the bottom here, and that the bottom isn't nearly as deep as you think it is. So you reach for, if you throw a penny in a pool or something and you're diving for it, you reach for the penny, and it's not where it looks like it is. If you're bow fishing or something, trying to shoot a fish with an arrow for some reason, it would look like the fish was there, but it would actually be closer to you and much deeper than you think it is. All right, so that's kind of an interesting little thing. Constructive interference is when rays of light or waves of light add up. You can see that these two waves are intersecting right there, and I've got a upward peak right there, a crest right there, and another crest. Those are going to add up. So here's two little waves, And when they add constructively, those peaks are going to match up and give me even higher peaks. And the troughs are going to add up, and those are going to be bigger troughs. So if the height of this one's 1 and the height of this one's 1, when I add 1 plus 1 right there would be 2. And this would be -1, and there's -1, so I get -2. I just double the amplitude if these are the same size coming in. I can also have destructive interference. So right here you can see 2 waves coming in, and when they meet, this one's at the bottom, but this guy is up here at the top. So I'm adding +1 and -1, and I'm getting 0. That's destructive interference, and it just totally cancels out. And we can say some more about that another day. But that's kind of what's going on with that diffraction pattern that we saw with the slit experiment, Young's slit experiment right there. Those waves are canceling out and giving us those peaks. All right, thank you very much, and we'll say more about all this next time. And